All right, good afternoon, everyone. We're going to get started with Over the Edge, Silently Owning Windows 10's Secure Browser with Eric Bossman. Please remember to silence your cell phones. Let's welcome Eric.
Hello, everyone. I'm Eric, and I'm going to be presenting work I've done as a PhD student at the VUSec group at the VU in Amsterdam. Let's turn on my... first, a warning. This presentation will be fairly technical, so you may encounter some pointers. I've tried to make it as easy to understand as possible without sacrificing the technical content. I'm going to present an attack where we will use memory deduplication as a software side channel and combine this with Rowhammer, a hardware bug, in order to create own Microsoft Edge without the use of any software bugs. If you want to know a bit more, we also have a paper called DDEP as Machina. So if I've left out details, you might be able to look them up in the paper. So what are we going to do? In short, we will use deduplication as a side channel to leak both heap and code pointers. So we will leak a heap address of a JavaScript array with contents we control, and we will leak a code pointer into a Microsoft Edge's a JavaScript library. And this will be enough for us to craft a fake object, but then we don't have, the object will still be in our in the data, so we don't have a reference to it. So we will use Rowhammer to create a reference to this object, and this will enable us to get an arbitrary read-write primitive from there. So for this attack, we make use of memory deduplication. Memory deduplication is a method of reducing the memory footprint of a system. It has been introduced first in virtualization environments. But starting with Windows 8.1, it was enabled by default in the operating system as well. So how does it work? So say you have, so in this case, the left side contains is a figure of the physical memory of the system. On the right side, you have the virtual memory of two processes. So, say both processes have the same image of the Mona Lisa in their address space. The operating system or the hypervisor can do a sweep and detect that both processes have the same page contents in their address space, and it can point both. Virtual addresses to the same address, and then free up the memory that was used by the second copy. Of course, now we have a problem. If process A tries to write to the data, it will also change in process B. That's why the operating system marks those pages as copy on write. But this opens, this enables to do another thing. So the main problem with this is that unlike other methods of reusing the same data in address space, like fork or file-backed memory maps, the deduplicated content doesn't have to have the same origin. So, and this opens the way for an attacker to use deduplication as a side channel attack. So, how does this work? So, if an attacker wants to know whether a certain memory page is present somewhere else in the system, the attacker can simply replicate this page, wait for a possible deduplication, and then write to it. So if it's not been deduplicated, it's not copied. It's not marked copy on write, and the write will just happen very quickly. If it's marked copy on write, all kinds of things will happen. And most importantly, the page has to be copied, and the page tables have to be updated. And in short, this takes way longer, and this can be detected from JavaScript. What this gives us is a 1-bit side channel, and the fun thing is, because these pages are deduplicated from all over the system, we can cross security. We can leak information across security boundaries. An attacker replicates a page, waits a bit, and then sees if it has been deduplicated. So it could be in a different virtual machine in the case of a hypervisor environment. And in Windows, it could be across processes. In our case, we will use this to leak information from within the process, but we will leak this information from within the JavaScript runtime. So we will leak information which is not available from the runtime. But first, we wanted to see what else we could do with this. So the most an obvious candidate is to use a covert channel. So in this case, we have Google Chrome and Microsoft Edge as two browsers, and we leak a short message from one process to another through the deduplication side channel. Another thing we can do is this is so here the two processes cooperate, but we could also do this for processes which do not cooperate. For example, we could detect what kind of software was running. So when we first started this, we thought, well, maybe we can find code pages, just find any executable you could get your hands off, and then pick some code pages from these executables, load them in your browser, and see which ones get duplicated. So it turns out to be a bit more difficult. So this is a memory dump of WordPad, and then we restarted Windows, so that the ASLR is all different. And so these are two measurements where WordPad wasn't running. So we see some deduplication of pages which are probably always in the system. And then when WordPad is running, we do see some extra pages being deduplicated. But it wasn't as good as we would expect it to be. We expected the code pages to be really clear and visible. So it turns out that file-backed contents are not deduplicated. So it's a bit more difficult for us to identify code. So you can probably still do it. Just manually go through a memory dump and see which pages are not file-backed, but always replicated in the same way. But it's not as clear. But you could still possibly do stuff like detecting someone running. Someone could possibly still use it to, say, detect that you're running your obviously legally obtained copy of IDA Pro, for example. So we thought, well, what about packed executable? So we took Skype, and Skype is a well-known executable which unpacks itself. So these are captures from when Skype is not running, and these are captures from when Skype is running. So it's clearly visible that there's lots of pages getting deduplicated. Viruses or malware usually also uses a packer, so it could be possibly the case that you could have a virus scanner from within the browser. But for our exploit in Edge, we need a bit more. So from up until now, we have a single bit exploit which can leak whether a complete page is present in memory. But that's not enough for to leak ASLR in general. So we need to find something better. So we want to see if we can leak arbitrary data, like a pointer or a password. And in this case, we need ASLR pointers. So the first problem is that the thing we want to leak is not as big as a page. So we kind of need a way to take the secret we want, so an ASLR pointer, and then make the system create a page which contains all known data except for the secret. So this might sound difficult, but say you want to leak something from a different process, you might be able to do I/O with this process, send the data, and then an application developer won't think about, well, I can probably not. So the fact that you can create a page in memory is not part of the threat model of the application designer, and shouldn't be, if you ask me. So you might be able to create a page which only depend on your secret that you want to leak. The second problem is that the entropy of the secret might be too big. So you need to, for every possibility, you need to create a page which is 400 bytes big. And then with the amount of bits of entropy you need, the size requirements go up exponentially. So what if you want to leak more than a high entropy secret? So you need a way to kind of only leak part of the secret at a time. So we have two primitives. One is the alignment primitive, where we try to push the secret just on the boundary of two pages, such that one page contains only part of the secret, and the rest is filled with known data. So we can leak part of the secret at once. We have a second primitive where we overwrite part of the secret. Say you have a page somewhere, and then the ASLR pointer somewhere, and then the allocated memory gets freed, and then you get a new allocation with a buffer where you can push data. You can push data up until a certain point, and then wait for deduplication. Push data up until a certain point where you overwrite part of the secret. So that's our second primitive. In our case, we will use the first primitive, the alignment primitive, to leak a pointer to the JavaScript library in Edge. So Edge JIT compiler compiles native code, and the function epilogue of this native code contains all known data except for a code address. So what we do is we create lots of functions which are just big enough to span just over one page. And then because JIT, Microsoft Edge randomizes the creation of, randomizes the size of the functions, we just spray it with a number of functions, and then some of those will have a code address which spans multiple. The code address will span multiple pages, and this way we can leak the secret in two steps. So first we leak the most significant random bits, and then when we know this, we can probe for the lower, the least significant random bits in the second stage. So now we have used this to get a pointer to the JavaScript library. So on the second, but we still need to get a heap pointer. So, and there's a problem. We're not able to use the first two primitives to get a heap pointer leaky pointer. We couldn't use alignment, which is kind of unusual because pointers are usually 4 or 8 byte aligned, so they won't span a page. And we didn't find a primitive where we could partially overwrite a pointer. So we had to find something else. It's also the entropy of a heap pointer kind of is bigger than the code pointers. So the advertised ASLR is 24 bits, but in reality there is all kinds of non-determinism that increase the randomness to say 36 bits, maybe a bit less, but so we needed to find a better way because so given that you have 24 bits of entropy, so it's 2 to the 24th pages, so 2 to the 24th times 4K byte pages, you need 64 gigabytes. So that's already not useful. And if you account for 36 bits of entropy, you need 256 terabytes, which is of course entirely feasible. And then to account for noise, you also need some redundancy. So you need to multiply it with some amount of redundant probes. So it's clear this is not possible. So what we first did was to employ a second side channel. We used the side channel for the allocation, a timing side channel for allocating objects. So in Java, in JavaScript, in Edge, if you allocate a small object, you get an array, an object, and a point which points to a buffer with actual data. And for small arrays, those are allocated together, probably for performance reasons. So these objects are then, So we actually interested in the data part of the object, but because they're allocated together, we can calculate it from a reference to the object itself. So these objects are allocated in using a slab allocator. Every pool is 16K in size, but every megabyte there's a new virtual alloc call which allocates an extra megabyte, and which gives us a timing side channel on the first allocated call. This first allocated object, and this object happens to be at the 1 megabyte boundary. So there we get our we reduce our entropy. So this is a figure of the timing it takes to allocate objects. So from left to right, from top to bottom. And we can see a lot of noise, but we also can see a clear signal. So the clear signal are so every 5,440 allocations, there's an allocation which takes longer than average, and we cross correlate these, so we find change of these. So we conclude that those are potential 1 megabyte aligned objects. So sometimes there's a garbage collection phase, and it shifts a bit, but then we can see, okay, there's another correlation here. There could also be some related delays. So here we have in the same allocation, we see another signal. So we don't know why this happens, but we just include it in our list of potentially 1 megabyte aligned objects, and for us that's no problem in our attack. So what we have now is we have reduced the entropy to 20 bits. So that would mean 4 gigabytes of memory, which is still too much. 4 gigabytes times the redundancy we want. So we need to find another solution to this. So to solve this, we make use of the same intuition as the birthday problem also called the birthday paradox. And this says that in a surprisingly small group of people, the chances of two people having the same birthday gets very high. And the intuition behind this is that you don't compare just one person with one person's birthday with the other people's birthday, but you're actually comparing everybody's birthday with everybody's birthday. And this is actually, when you think of it, exactly what the deduplication mechanism is doing. It's a machine a weird machine that finds copies, finds identical copies and combines them. So this fits pretty well. So we can, if we have multiple secrets that we want to know, we can create those in the address space, and then we create probes that of secrets that might be in the address space, and then once there's a cross correlation, the operating system will merge them, and we can detect this. So how does this work in practice? We have our list of 1 megabyte aligned objects, or potentially 1 megabyte aligned objects. And then we take an array, and we create references to these objects, which happen to be pointers. So we we now have pages with secrets in them. So so these pages encode the secret that we want to leak. On the other hand, we use a typed array, which in JavaScript allows us to control the memory completely, to fill that array with pages which look like the same array pages, but they have with addresses of guest objects. So these objects, and then we don't use 1 megabyte aligned objects, but larger objects, 128 megabyte aligned objects. And then we cover the entire address space with this. So we have pages which cover the entire address space. So we kind of now have created a divide and conquer strategy. So on one end, we have we have allocations which are close together, which with real addresses, and then guesses which span the entire address space. So we kind of have we don't need ON memory space complexity, but we can take the square root of this. So when we have this, it gets deduplicated, and we can test, and we find one of our objects, which is enough for our exploit. So we have one object for which we know the address. So now we have leaked heap and code pointers. Now we can create a fake object, and then we'll use rowhammer to flip a bit and create a reference to this object. So the object we've chosen to create is a typed array, which allows us to basically manipulate any code, any writable code in the address space, read data. So what we do is we create this fake object in an array for which we know the address, and then we use rowhammer to flip a bit in a reference to another array to create a reference to the object that we want. And if we have that, then we're basically there. So we use rowhammer for the we use a hardware vulnerability called rowhammer to get this bit flip. So for rowhammer, the observation is that if you read a memory address so memory is divided in rows, and if you read a row repeatedly, if you cause the hardware to read a row repeatedly, neighboring rows will leak charge at a higher rate than normal, and if you're lucky as an attacker, bits will flip in neighboring rows. So we're using this to hammer arrays of references to objects, and where if we find one where a bit flips, we can flip a reference to the right array. We can flip a pointer to a fake object. In our paper, we also describe a second version where we flip a bit in a double value, which allows us to change a double value into a pointer. And combining those two, we can use 23 bits out of every 64 bits in memory to create an exploit, to exploit, which means roughly 1 in 3 memory bit flips will yield a valid exploit. So there have been lots of software. Well, there have been some attempts to mitigate rowhammer in software, but it's a pretty hard problem. For luckily, mitigating memory duplication is a bit easier. So we suggest just to disable memory duplication, and this is also what Microsoft have done in their latest update. Although you won't see it when you try it. But we don't notice any deduplications anymore. So the takeaways are memory deduplication is a way more powerful side channel than previously thought. If you optimize try to optimize memory usage both by shrinking the memory technology in hardware as trying to reduce its usage in software, it might come at a price. And finally, even without bugs in your browser, you might still be owned. In this case, using deduplication and rowhammer. If you want know more about this, we have a website on this project. We also have other projects which might be interesting to you, also on mobile security and cloud security. And now I'll show a demo. So in Windows, deduplication happens every 15 minutes. So it's a recorded demo, because it might take a bit long. So here we have started the deduplication. It's now doing a sweep. So we have created pages which will allow us to detect heap pointers and code pointers. So I'll skip until the first page here. You can see it has found actually 2 heap pointers, and this is a bit annoying. So it has found actually code addresses. So actually this is a mask which is applied. So it's actually these two these two signals don't detect anything else than that are pages which don't contain any secrets. But starting from here, we found the first byte and the second byte in the first phase. And we go further. Doing the second deduplication cycle, we have found the complete address. After that, we start a row hammer attack, for which we first have to find cache eviction sets, and then this also no. I'll just let it run. It's maybe good to show. So this attack will work pretty fast, but that's because for the capture we reduced the refresh rate of the memory modules to quickly give us bit flips, but we've now also we also have can now create bit flips using the native refresh rate. Okay, now it has found all the cache sets. Actually, it missed a few, but it's still okay. So now I think in a few moments it will find a bit flip, and it will be a bit flip, which has the correct. So now it's stopped. So I think it's now hammering. And then when it's done, so here, actually the error, the log message wasn't updated, but here it found a bit flip. In this case, we can change the double into a pointer value, and then we do our hammering, and the end result is an array buffer object which points to another array buffer object. So we can basically change where the one array buffer object points using another array buffer, and then we basically say, okay, I want to read this piece of memory, or I want to write this piece of memory, and that allows us to get control over the process. So that was the demo. So, any questions? Okay, thank you.